Problem number 4. So we have a table that's partially filled in. We want to fill in the rest of it in such a way that it would not represent a function. The definition of a function, each x value has to be paired with exactly one y value, one output. There's lots of different options I have here, but the bottom line is I need to have an x value that ends up with more than one y value for this not to be a function. For example, what if I repeated the input of 2 here? 2 is going with 7. Well, as long as I fill in any number except 7 in this box, I'm going to violate the definition of a function. I'll put a 6 in there. You can't have 2 coming in and sometimes giving you 6, and here 2 comes in and now gives you 7. That's no good. That's not a function. I can fill in the other numbers however I want. I've already violated now the definition of a function. The moral of the story, if you have repeated x values where the y values are different, you don't have a function. Problem number 5, I want to label the missing tick marks here. I've been given the first value and one other value, but it's really even better than that. The first value in each case is 0, and then I've been given the fourth tick mark out. That makes this process very easy. If there are 4 spaces between 0 and this number, all I'm going to have to do is cut this number in half, and I'll know the second tick mark here. Well, half of pi over 2 is just pi over 4. And then to find the first tick mark, I could just cut this number in half. Half of pi over 4 is pi over 8. I'm doing that in my head, but of course all you have to do is multiply by 1/2. Once you have the first tick mark, you're basically done. You can get all the rest by simply counting by pi over 8. This is 1 pi over 8, 2 pi over 8, which has reduced, followed by 3 pi over 8, 4 pi over 8, which reduces, then 5 pi over 8, and then 6 pi over 8. 6 pi over 8 reduces to 3 pi over 4. I can do the same thing in letter B. Pi over 3 here, half of that would be pi over 6. Half of that would be pi over 12. Now I know I'm counting by pi over 12s. So I've got 1 pi over 12, 2 pi over 12, 3 pi over 12. Now 3 pi over 12 reduces to pi over 4. 4 pi over 12, which has reduced. Next would be 5 pi over 12. And then 6 pi over 12 reduces to pi over 2. And I've filled in my number line. Problem 6. We're given a trig statement here. We know the ratio. We don't know the angle. We want to find the angle by hand using a picture. Well, the key here is we know that in each case, theta is an acute angle. That means between 0 and 90. It's right there in the first quadrant. So a quick triangle picture in the first quadrant should give me my answer. Let's see. Sine theta, well, sine is opposite over hypotenuse. If I'm to do this by hand, this must be one of our special triangles, and of course it is. It's just the 30, 60, 90. The angle opposite the root 3 is 60 degrees. That's what theta is. Now they want the answer in radians. 60 degrees in radians is pi over 3. Cosine theta equals 1 over root 2. Again, first quadrant. Let's see, cosine is adjacent over hypotenuse. This is one of our special triangles. It's the 45, 45, 90 special triangle. So theta is 45 degrees, or in radians, pi over 4. And then the final example, let's see, again, first quadrant, tangent, opposite over adjacent. Here's my angle. It's another 30, 60, 90. This time the angle is opposite the 1, which means it's 30 degrees, or in radians, pi over 6. In problem 7, we're essentially asked to do the same thing, except this time using the calculator. Theta is still acute, which is very helpful. We know it's between 0 and 90 in terms of degrees, but these are not nice values. We could draw the same pictures we drew up here, but it wouldn't help because these values aren't associated with special triangles. So we'll just go to the calculator. We've already learned a button on the calculator where if you know the ratio, you can plug that in to figure out the angle. It's the inverse trig function. So if I want to get theta, as long as it's in the first quadrant, those buttons work very easily. Simply take the 1/6 and plug it into the inverse sine function. What comes out will be the angle. Now, the directions do say that they want me to do this in radian mode. So I'll go to the calculator. I am in radian mode, and all I have to type in then is sine inverse of 1/6. Here is the acute angle in radians that generates that ratio. To 4 decimal places, it's about 0.1674. For letter B, we'll be typing in cosine inverse of 0.37. 0.37 is the ratio. We're looking for the angle. So cosine inverse 0.37 comes out to be 1.1918. And letter C, I'm going to have to type in tangent inverse of 9. So tangent inverse 9, and that comes out to be 1.4601. And so we found the 3 angles we were looking for. And then finally, number 8 is related to these last 2 problems. I've got a couple of statements here. Sine inverse of A equals B, and then cosine of C equals D. Some of these letters represent angles. Some of them represent ratios. Let's start with the regular trig statement. Cosine of C equals D. Well, trig functions always take in angles, so C must be an angle, and they send out ratios. The cosine for angle C is the ratio D. Of course, we know that in the inverse functions, everything is reversed. Inverse functions take in the ratios. So A there is a ratio, and they send out to you the angle. So B must be an angle. And you can see that even in problem 7, right? We put in the ratio, we got out the radian angle.